So if we think of, if you remember, I talked about different types of analytics, and I talked about when we use analytics to look at the past in terms of descriptive analytics, and we use analytics to look at the present and the future, then you'll find that regression analysis is used often in predictive analytics for trying to make predictions about what's going to happen in the future in terms of the relationships between variables. So let's get into it. So bivariate analysis is when we are interested in making a relationship between two variables. So for example, is this variable related to another variable? And the measure for that often is called correlation. So two things might be correlated. But in regression analysis, we're actually looking for a stronger relationship. We're actually looking for a causal relationship. So if one variable increases, that causes another variable to increase. So it's concerned with the relationship between two variables. It's often used in situations where we wish to predict useful results from existing data that we already have. So for example, predicting customer behavior using existing data or application forms. So we have data about our customers, and we want to know if we can use that data to predict their behavior, because that will help us in our marketing, for example. Or we collect data from a prospective customer and we want to know if that data enables us to predict how that customer will behave. So for example, you fill in an application form for a loan from the bank, and then the bank can look at your application form and make a prediction of the risk you pose to the bank, for example, or how reliable you would be. And banks have got very, very good at making those sorts of predictions. Demand analysis, so how many units customers will purchase, for example. Estimate of how many policyholders will be involved in accidents or be victims of burglaries. So insurance companies have been doing this type of regression analysis for many, many years, because that's how they determine what your insurance premium will be. Estimating how the performance of an individual company quoted on the market is related to the overall stock market. So regression is used to judge the volatility of a particular stock. So for example, if the stock market does well overall, some businesses do really well. But if the stock market goes down, then they also do really badly. So if your investment strategy is to avoid risk, or you think that the stock market might be heading down, you would avoid those sorts of stocks. But some stocks are unaffected largely by the stock market. So for example, supermarkets tend to be largely unaffected by changes in the stock market. So for example, we've seen that the stock market has gone down significantly in the last few months, but actually people are still going to the supermarket because we have to eat. Okay, so, and in fact some supermarkets actually have a negative relationship. So for example, if in hard times supermarkets like Aldi and Lidl actually do better. Okay. Understand the relationship between wait times of callers and numbers of complaints in a call centre. Okay, so for example, lots and lots of companies have call centres. They're constantly trying to determine how many members of staff they should have in the call centre, and they know that if they have fewer members of staff, then the service will be poorer and they'll get more complaints. So they can start to map the relationship between numbers of people in the call centres and complaints, and they can try and find what's a nice balance between those two things. understand the relationship between oven temperature and shelf life of biscuits baked in the oven. So regression is used a lot in manufacturing and food production, because often the relationships between, for example, time in the oven and the quality of the biscuits is a causal relationship. So there's just a few examples for you. Now, how do we do it? Well, the process of regression follows this. First, we try and articulate our problem in the form of a research question, and then we try and develop hypotheses. Okay, so we try and actually develop a theory as to why one variable would be linked or causally linked to another one. This is because it's very easy these days just to play around with the data. And of course, yes, we do play around with the data a bit. But the trouble with playing around with data is that you might find relationships in the data which are not actually causal relationships, and you could make some mistakes. And I'll talk about that later. So we should develop a hypothesis as to why one variable should influence or cause changes in another one before we start to actually look at the data. Then the golden rule is you must look at a scatter diagram first. Before you start pressing buttons and doing regression, you should look to see if there is a relationship there that you can see on a scatter, because if it's not there in the scatter, then it's not there. And sometimes people will use, because it's so easy to do regression on computers these days, they will just get the results and say, "Ooh, that's a good result," and actually they don't see the real relationship, and I'll talk about that later as well. Once we know that there's a relationship between two variables, then we can actually create a model. And the model is just a way of summarizing the relationship between those two variables so that we can use that in the future to make predictions. And that's it. That's the process of regression. Okay, so let's just go back and just have a look at a scatter plot. Here we've got a scatter plot whereby we've got rent, values for rent on the x-axis and survival costs, or the cost of living, on the y-axis. So our hypothesis might be that the survival cost at a particular university might be dependent upon the rent cost, and so there might be a relationship there. So universities with high rent costs might be indicating that the cost of living at those universities would also be high. So we might expect to see a positive relationship there, where universities with high rent would have higher survival costs. Now, when we actually look at the scatter plot there, we can see that there actually isn't a very clear relationship there at all. There might be a slight positive relationship there, but we can see that those two variables are not clearly related, and the data is spread all over the place. So actually, when we look at that, we say actually there's very little relationship there, and so we would not be able to use this relationship to make predictions about survival costs. The reason for that is actually rent costs are more dependent on the popularity of the university. So highly popular universities will charge higher rents, and actually the survival costs are more dependent upon the location of the university within a city or a rural area. And so survival costs depend on other things. They depend on the local authority and the local economy, whereas rent cost is dependent upon the success of the university. So that's a good example of a relationship that we can see from the scatter is not clear. We assume the y variable is dependent upon the x variable. Okay, so this is how we structure our scatter plots. So we talk about the variable on the x-axis as being the independent variable, and we talk about the variable on the y-axis being the dependent variable. And the reason for this is that the way that we express our hypothesis is that we say if the x variable increases, then the y variable will increase, and that would be a positive relationship. Or we might say if the x variable decreases, then the y variable will decrease. Or it could be that when the x variable increases, the y variable decreases, and that will be a negative relationship. And so that's just the way that we express it. So the independent variable and the dependent variable on the y-axis. And what we're arguing is that the y variable, or the dependent variable, is dependent upon the x variable. Now let's look at another example. So let's say that our x variable is local authority population, and the y variable is the cost of recycling in that local authority area. So our hypothesis might be that the cost of recycling within a local authority area will depend upon the population size of the local authority. So if there's more people in the local authority, then the cost of recycling will be higher. That makes sense, doesn't it? More people equals more waste, which means more cost of recycling. And when we look at the scatter plot, we can see that there is a positive relationship. We can see that the graph, the data is going up, and so the scatter plot is supporting our hypothesis that cost of recycling depends upon local authority population. But notice that it wouldn't be the same the other way round. Okay, so local authority population doesn't depend upon the cost of recycling. If the cost of recycling goes up, people don't have more children, or people don't go, "Ooh, look, the cost of recycling has gone up. Let's go and live there." Okay, so cost of recycling depends upon population, but population doesn't depend upon cost of recycling. So regression will automatically fit a linear or a non-linear line to your scatter plot for you and produce the model too. And the strength of the relationship can be measured by using the R-squared value. So an R-squared of 0 means no relationship, it's just random. And an R-squared value of 1 is a perfect relationship. Normally we look to work with R-squared values between 0.7 and 0.95. But it depends on the context, and this is where the analyst needs to show some judgment, because when you're doing large scale analyses, so large multivariate regressions, researchers might be content with much lower R-squared values like 0.3 if that supports their research. So a lot depends on the context there. It depends on how you're going to use the model, whether you're just looking to see trends in data or whether you actually want to make really precise predictions. So the next question is multivariate analysis. What is that? So multivariate analysis is really very similar to bivariate analysis, where you've got two variables. But let's say we're looking at a relationship between local authority population and cost of service, like we were before, and we said that population was the independent variable and that the cost of the service depended upon the population of the local authority. But what if there was another variable which also affected the cost of the service? So for example, here we've got two local authorities. They have the same population, but they have different costs of service. So can we explain that? Well, with some local authority services, for example, the population is the major variable, but also area of the local authority can affect costs. So for example, if the service includes delivery or travelling, then the travel costs will be higher if the local authority area is larger. So we would want a model which had both population and area. So if two local authorities had the same population, but one was bigger, then the one with the bigger area would have a higher cost because it involved travelling costs. So a better model would be a model which had both population and area that predicted cost of service. And that's what we call multivariate analysis, i.e. there's multiple variables being used to predict the cost of service. So including another variable means that our model changes slightly. So instead of y equals mx plus c, it becomes y equals mx1 plus nx2 plus c, where x1 is one variable and x2 is the second variable. So for example, cost of service equals m times population plus n times area plus c. So if the relationship between or if the relationship does really involve two variables, then this particular model is going to be better at predicting cost of service. Now, population here would be the dominant independent variable, but including area just simply increases the predictive power. Okay, so multivariate models are very popular these days because they're so easy to do these days in the software, but you just have to be very careful with multivariate because people can get a little bit carried away and the interpretation of them is sometimes difficult. Now, regression is great, but you need to be a little bit careful because it's so easy to do that you can find relationships, but actually sometimes those relationships are what we call spurious relationships. What that means is that there is a relationship between two variables, but it's not causal. So let me give you an example. So you may find a good relationship between two variables, but actually they are both related to a different variable. So for example, women on hormone replacement therapy have lower levels of heart disease. Okay, so if you look at the data, you'll see women on HRT have lower levels of heart disease. So therefore, you might say, ooh, great, so hormone replacement therapy is good for heart disease. Actually, no, there is no causal link between HRT and heart disease. Actually, women on HRT tend to be thinner, richer, and have healthier lifestyles, and that is what causes the lower levels of heart disease. Another example, men who shave a lot are more likely to have a heart attack. Okay, now that sounds crazy, doesn't it? Shaving weakens your heart? How is that possible? Hairy men have weak hearts? No. Vain men have weak hearts? No. Of course, there's no causal link between shaving and having a heart attack. But actually, if you look at the data, they are correlated. Why? Well, the reason is because men who shave a lot tend to have more stressful jobs and more stressful lifestyles. And it's the stressful lifestyle that leads people to have higher tendency towards heart attack. So if you look at the data between shaving frequency and heart attacks, they are correlated, but it's not a causal relationship. It's just a correlation. So just be careful. If you find a relationship between two variables, you need to think about whether that relationship is really causal or whether it's just a correlation. And that's particularly important if you are trying to build theoretical models. Now, the final thing I want to say is that you must always look at a scatter. Now, I know I've said that a few times, but when you're doing regression analysis, because you're looking for causal relationships and you want to make reliable predictions, you must always look at a scatter before you collect your model and your R-squared. So this is why. Look at this data. So we've got 4 data sets there. If you did a regression for all of those 4 pieces of data, you would get the same model, y equals 0.5x plus 3. So they all have the same regression model and they all have the same R-squared of 0.67. So therefore you'd say, oh, well, there you go. That model is equally good for all those 4 data sets because the R-squared is 0.67. No, because when we look at the scatter, what we see is that only one of those data sets is the model a reliable summary. Okay, so if we look at the top left scatter, we can see that the model is perfectly summarizing that data. Okay, so we've got data which is showing a nice positive linear relationship, and the model is perfectly summarizing. But if we look at the top right, we can see that that model is not summarizing that data accurately. Actually, the data is showing a non-linear relationship. So as the x variable increases, we do get a positive, but actually there is a curve and then it starts to come down. So that model is not accurately summarizing that data. And actually, we should be choosing a non-linear or a curved model to summarize that data. Now, if we look at the bottom left data set, we can see that actually there appears to be an error in the data. There does appear to be a very clear, strong, positive linear relationship between those 2 variables, but one of the data points is actually completely different, and it looks like an error. It looks like an outlier, we often call it. So that outlier is actually pulling the model up a bit. So if we saw that or something like that, we would immediately go, hang on a minute, I need to go and see what's going on with this data, and I would want to look at that data point to find out if it was an error. Now, if we look at the bottom right data set, we actually see that something really quite strange is going on there. There actually doesn't seem to be any clear relationship there at all. All of the data points are actually have the same x value. So actually we can't build a model if all the x values are all the same. So actually we would need to go back and say, hang on a minute, we need a range of x values to see if there is a relationship between x and y. And the only reason we've got a model is because, again, we have an outlier. Or maybe it's just that high value of x is correct, but we just need to collect more other values of x to see if there is a consistent model there. But we can't use a model which has been built with that data set. We need a more of a spread of data. So it's absolutely crucial when you're doing regression to have a look at a scatter, because that will show you very quickly whether the relationship is strong or weak, whether it's linear or non-linear, whether you have a nice spread of data so that you can actually reliably develop a model. So that's a little introduction to regression. It's a very popular approach, but the main things to remember is that with regression, normally we're looking for causal links between the variables, and the way that we express that is we say that the y variable depends upon the x variable. Now, you can use regression analysis to look at other types of relationships, and we'll actually do that in the next recording when we actually look at forecasting. Okay, thanks a lot.